Welcome to KCD Bengaluru. My name is Madhav and I'll be talking on imperative, declarative, and Kubernetes. The main idea of this talk is to get an intuitive understanding of some of the core design principles of Kubernetes. So we'll start off by asking the question, what even is Kubernetes? Then we'll look at some intuitive way of looking at what imperative and declarative systems are. We'll formalize things just a little bit to try and build a mental model of things. Then we'll do a small demo to try and understand the differences between imperative and declarative a little better. Then we'll map that mental model that we created to how Kubernetes actually does things today. And then we'll take a step back and review some of the things that we learned. So what even is this thing called Kubernetes? When I first started off, I didn't really know why Kubernetes existed or why it was built the way that it was. So on going to the documentation, one of the first links that come up is what is Kubernetes. So if you click on that, this is what you get. And I realized that I wasn't sure I understood what the sentence meant. I understood parts of it in terms of I understood what extensible meant, what managing meant, what containerized workloads meant, but I wasn't sure what this whole thing together meant entirely. So I thought, okay, let's break it down into smaller bits and try and understand some of these smaller parts. So if you were to break it down, it would look something like this. So why is Kubernetes extensible? Why is it good for managing containerized workloads? What is declarative configuration and why does it do it? Why is Kubernetes good at automation? So today's talk on a high level is structured something like this. We'll talk about what imperative and declarative APIs are, what their differences is. We'll talk about what the controller pattern of doing things is. We'll talk about what self-healing means. And then finally, we'll talk about how Kubernetes fits into all of this, meaning that why did it take the controller pattern? Why did it take the declarative API? And how does it do self-healing? So imperative systems, let's try to get an intuitive understanding of these things. Imperative systems describe how you want to achieve something. So let's say our goal is to go on a vacation. So you as a person know what your goal should be, meaning that you do some initial research in terms of what your budget is, where you want to go, what you want your living arrangements to be like, and what you want cuisine, if you have any cuisine preferences. So having known your goal, you describe how you want to get there, meaning that you do step A first, then do step B, then do step C to finally reach your goal. But on the other hand, a declarative system would work something like this. Again, you know what your goal is as a person or as a user, rather. You know what your goal is. You describe that goal, you describe what you want to achieve to something like a travel agent. And the travel agent will try to make sure that whatever you have described to them, it works towards making sure that what it delivers is as close to what you described as possible. It might not be exactly what your expectations were, but it tries to make sure that you reach you reach your goal, which is to go on a vacation. So is it really an either or type of situation here? Meaning that if you are using a declarative system, are you not dealing with an imperative one at all? The answer is no, because usually what happens is a declarative system usually has some form of an underlying imperative one. Meaning that, let's say our goal is still to go on a vacation, you describe what you want to something like a travel agent, but the travel agent here again would act like an imperative system, meaning that it internally has these certain steps defined to make sure that whatever you've described, it tries to work towards getting you there. So in general, the trend is somewhat as follows. If you move more towards the declarative realm of things, you get more abstraction. But if you move more towards the imperative realm of things, you get more control. So if you were to build systems that have a lot of that can experience changes which you haven't really taken into account for because you can't predict them or you can't think of them well in advance, but you know for a fact that you have mechanisms in place that can recover your system, and you don't really want your users to see these temporary failures. So having a more abstract system in that case is the way to go, and a declarative system is the way to go. And Kubernetes is a perfect example for that, as we'll soon see. So let's formalize things just a little bit. to try and build a mental model of things. So this part is largely inspired from this amazing blog post by Dominic Dornoff called Imperative versus Declarative, which I've linked towards the end. And I would highly recommend reading that as well. I've changed a few things to try and make sure that the terminology matches some of the other resources on such topics that are out there. So let's try and understand this mental model with the help of an example by keeping in mind an example of a thermostat. Using a thermostat, you can either increase the room's temperature, you can decrease the room's temperature based on if you want it hotter or cooler. So let's say that the system state, which is what your room temperature currently is, let's say that the room temperature currently is 23 degrees Celsius. That's your system state. But you also have a desired state, meaning that I want my room to be 25 degrees Celsius at all times. And the ultimate goal is to try and get the system state and the desired state as close as possible. Ideally, it should be the same. Now, you also have a machine which takes a command and acts on that command and tries to change the system state. So this command can be something like increasing the temperature of the room by 2 degrees Celsius to make sure that the current temperature, which is 23, increases by some amount to get to where you want it to be, which is 25 degrees Celsius. And who issues these commands? It's the agent. And the agent issues these commands by knowing what the desired state is. Now, apart from all of this, you also have the environment factor of things, meaning that there can be changes to your system state which are unintended, which aren't caused by a command that the agent issues. So these changes aren't accounted for because they can't be predicted well in advance, or they can be of such variety that you can't possibly think of all of them exhaustively. So the goal would be to build a system that even if having such environment changes and such unintended changes, your system should still be able to recover and drive itself towards the desired state. Even if it doesn't do it immediately, it should still move in the right direction. And the agent also gets some form of feedback from the system saying that this is my state currently. And the agent issues commands knowing both the system state and the desired state, meaning that if I know that my desired state is 25, and only if I know that my system state is 23, can I issue a command saying that I want 2 degrees more of temperature, because you won't really have a frame of reference if you don't know both of these things. And this sort of loop is known as the control loop pattern, meaning that you get some form of feedback, you know where you want to go, and based on that, you adjust your trajectory of actions. And in an imperative way of doing things, the agent is the user themselves. So something like me manually going and increasing the temperature or decreasing the temperature to make sure that the temperature in the room is ideal. But in a declarative way of doing things, the agent is the controller, is something known as a controller, meaning that the user still exists and the user still knows what the desired state is, but the user gives the desired state to something known as the controller, which sees what the current state of the system is, which sees what the desired state is, and it calculates some action to make sure that the machine executes a command that drives the system state as close to the desired state as possible. So this can be something like a sensor. So you set what you want your temperature to be, that is 25. The sensor senses that, okay, the temperature right now, 23, is lower than what I want it to be, which is 25. So it automatically issues a command saying that increase the temperature. And this is also known as a reconciliation loop. And the process of getting the system state to the desired state is something known as reconciliation. And as I mentioned, the command is usually based off the system state and the desired state. And also, again, you get feedback from the system state to the agent, which in a declarative case is the controller. Now, a small demo to try and further understand the differences between imperative and declarative systems. So for the purposes of the demo, I wrote a tool called KCD Cuttle, which should help us understand these differences a little better. So what I want to do is I want to say that, okay, I want 2 containers running at all times, and I want this image to be run by the container. I also want a load balancer in front of my containers, and the load balancer should use this image. And these are the ports that I want the load balancer to use. So that would look something like this. So I mentioned I want 2 replicas at all times. I mentioned what image I wanted to use and the load balancer configuration. So let's say, let's go with a declarative way of doing things first and see how that works. And as just to make sure I don't have anything running, I don't have any containers running initially. So if I do a declarative mode of doing things, the first step is something known as bootstrapping, which is just to create the load balancer, and it also creates a Docker network. What the Docker network does is it attaches all of the containers to the Docker network so that they can communicate with each other. And here, as you can see, it starts the controller. As soon as the controller starts, it gets feedback saying that I don't have anything running right now. I have 0 containers running. I need 2 containers running. So what I need to do in order to get to where I want to be is I need to spawn 2 more containers. So it spawns 2 containers, spawn 1, spawn 2, and both those containers are spawned and the state is reconciled. So now if I do Docker PS, I should sure enough get 2 containers running and 1 load balancer. And if I do curl, I should get hello from that host name. And if I let's take the environment factor into consideration. So let's say a container dies, right? So if I were to kill a container, this is something that I obviously don't want. This is unintended. So if I kill a container, it gets feedback saying that, oh, a container a container is down, and I currently have just one. I need one more. So it issues a command saying that spawn 1 more container, which it does, and the spawn is successful and the state is reconciled. So if I do Docker PS, I should get those containers back. So that's the declarative way of doing things. But if I wanted to do it imperatively, this is how it would go. So let's clean things up a little bit. So if I do Docker PS, I don't have anything running. So if I do kcd kotl apply, but let's do it imperatively this time. So again, first step is bootstrapping. I could have made the bootstrapping step also imperative, but let's assume that bootstrapping also happens. Now it says that my desired state is 2, but I am the agent currently, which means I haven't issued a command, so it won't do anything on its own. So it says it's awaiting reconciliation. So to make sure that I get to where I want to be, I can I can spawn a certain number of containers. So I am seeing that the desired state is 2. I am seeing that the current state is 0. So now I am calculating a diff of 2. So I spawn 2 containers. And once they are spawned, I can see that it says state is reconciled. So if I do Docker PS, I should get 2 containers and 1 load balancer. And then if I do curl, I should get those host names again. And let's do the environment factor of things again, right? So let's kill a container. If I kill a container, it gets feedback saying that 1 container is down. These events occurred. My current is 1, my desired is 2. I'm awaiting reconciliation. Please do something. So I am the user. I am supposed to spawn the command. I'm supposed to issue a spawn command. So I know what the state should be. So I know 1 more is required. So I have control over how many I should spawn. So you have more control here. And this is a very small example, but in something like Kubernetes, this makes a very big difference. So I spawn 1 more container. Spawn says it's successful, and it says state is reconciled. So things are working great again. So if I do Docker PS, I get that, and if I do curl, I get my host name back again. So that's how things work in an imperative and a declarative way. The differences are, in a declarative system, the agent is the controller. In an imperative system, the agent is the user. And if you have a lot of unintended state changes that can happen, a declarative system might be a better choice of design. So coming back to this, let's try to map these concepts to Kubernetes. So the machine is the API server, something known as the API server. The desired state, which from a user's perspective is usually described in terms of YAML files. The desired state from the system's perspective is usually stored in etcd. which is the backing key value store of Kubernetes. The system state can also be thought of as stored in etcd. And feedback in Kubernetes is received using something known as informers. And so whenever something is created or deleted or updated, that particular feedback event is received through informers, and the controller has logic to react to some of these events. So if something is created, what should I perform to make sure that I'm doing my job correctly? So feedback is received in terms of informers. So let's dive a little deeper into how Kubernetes does things using these concepts. So before we start, just a quick interlude. So pods in Kubernetes can be thought of as the fundamental unit of work. If you want to run something in Kubernetes, you create a pod. A pod is a concept in Kubernetes, which is, and at its core is just it's a set of containers basically. A replica set, on the other hand, is something that ensures that a certain number of copies of those pods are running at all times. So in our demo, we said that we want 2 of these containers running. In Kubernetes, you say that create a replica set where it ensures that I have 2 pods running at all times. A deployment is just a means to create and update pods and replica sets. A node is a worker machine in Kubernetes. The API server is the heart of Kubernetes, meaning that it exposes the Kubernetes API, which all of these components interact with. And it's also the front end, which we'll see what it means soon. So the Kubernetes machine, you have the API server first. The user comes and says that I want to create this deployment. Now, it's okay if you don't understand what this YAML means and what this command means. What is important to note here is that the user is saying, I want 3 replicas of my pods at all times. Now, the user gives their desired state to Kubernetes. The API server puts this desired state into etcd. So it's created the deployment object inside etcd. Now, there are also a bunch of controllers that come in Kubernetes that ship out of the box for you. And for the purposes of this example, we'll look at 3 controllers, which is the scheduler, the deployment controller, and the replica set controller. The scheduler's job is to see that a node is assigned to a pod, meaning that if you have pods in etcd which don't have a node assigned to them, the scheduler will go ahead and assign those nodes. Basically, it will schedule those pods onto those nodes. And we'll see how that actually gets scheduled and how it works. The deployment controller's job is to watch deployment objects in etcd, meaning that it will watch for changes and creations and updations and deletions of these deployment objects. And the replica set controller's job is to watch replica set objects and make sure that a certain number of those copies are always running at all times. And each of these controllers are responsible for their own objects. None of them will create an object or change an object which it isn't responsible for. So there is a clear isolation and a clear separation of concerns for all of these controllers. And this is important because let's say a certain pod goes down, let's say a certain controller crashes, it shouldn't affect the working of the rest of the remaining controllers. And then you also have these nodes, which are the worker machines in Kubernetes. And each node has a node agent called the kubelet, which is running on them. A kubelet has a control loop. So for the purposes of the example, we'll consider the kubelet as a control loop. And the kubelet also has capabilities to create and tear down pods and the containers in those pods. So the kubelet manages things on its node. So now the general control workflow looks something like this. The general communication workflow looks something like this. Now a deployment is created. Now the deployment controller sees that a deployment is created. The deployment says that I want 3 replicas running at all times, but there is nothing there. So it creates a replica set object, which is responsible for making sure 3 replicas are running at all times. It creates a replica set object. Now the replica set controller sees that a replica set object has been created, but my desired state is 3. My current state is 0 pods because no pods are created. So what it will do is it will go ahead and create 3 pods. So once these 3 pods are created, its job is done. And if you notice, the deployment controller does not touch pods at all. its job is to create the replica set object, which it does, and then the replica set controller goes ahead and does its thing. Now the scheduler sees that 3 pods are created, but none of them are scheduled. So by using some criteria and some algorithm, it will assign nodes to these pods. And let's say the nodes are assigned in this manner: pod 0 goes to node 0, pod 1 goes to node 0, and pod 2 goes to node 1. Now, the kubelet is also watching etcd for changes. Now, the kubelet sees that there are pods in etcd that are supposed to be running on its node, but it's not. So what it would do is it would go ahead and get those changes. Once these pods are scheduled, these pods become part of the kubelet's local desired state. So the kubelet caches this desired state, and all of these controllers have caches, and periodically they sync up with what is there in etcd. So etcd is the main source of truth here. The kubelet makes these pods part of its desired state. So if you notice, Kubernetes is not only distributing computation, but it is also distributing responsibility and the desired state. And this is very important because if something were to go down or something were to go wrong between the nodes and the API server, let's say the network connection breaks or there's a network partition that occurs, it's okay because the kubelet has local desired state now. So if something were to go wrong on its node, it will make the changes to make sure that things are back and running up again, which we'll see now. Now the kubelet sees that my local desired state has pod 0 and these pods, but nothing is running. So what it will do is it will go ahead and start those pods, meaning that, okay, now my local desired state is matching my current state. So things are working good for the kubelet. Now let's say that network partition which I was talking about occurs. And also pod 0, something goes wrong, a container in pod 0 crashes or something in pod 0 doesn't match how it's supposed to be. And that's okay because the kubelet doesn't need to see what's in etcd to make sure that it's getting what the desired state is supposed to be, because Kubernetes has distributed the responsibility and the desired state as well. So now it sees that my desired state is 0 and 1. It doesn't need to immediately see doesn't need to immediately contact the API server. It's able to manage what is there locally. So whatever the latest local desired state is, it will maintain that. So now that it sees that pod 0 is supposed to be running, but it's not, so the kubelet can go ahead and restart that. And it does. And this is what self-healing is. So whenever these unintended changes happen to your system, these control loops or this controller pattern is trying to make sure that if a change happened to its object that it's supposed to be maintaining, it will make sure that it self heals and things in the system work the way they're supposed to be this change doesn't need to be immediate. So Kubernetes Kubernetes always says that I will eventually get you where you want to be in terms of your system state. So eventually the system state will match the desired state. And this is how Kubernetes does self-healing, by distributing the desired state and also by distributing responsibilities and having these isolations in place, meaning that this controller is supposed to be only for its own object and it shouldn't interfere with other controllers objects as much as possible. Now, let's say the user says that I want to scale up, I want to scale out, and I want 4 replicas of my pods now. So the API server will edit the deployment. Now the deployment controller will see that the deployment has been edited and the new desired state is not matching my current system state. So it will go ahead and edit the replica set object. It will not create another pod because that's not its responsibility. So it will edit the replica set object. Now the replica set controller will see that, okay, the replica set object has been edited, but currently my current state is not equal to the new desired state, which is 4 pods. So it will create another pod and its job is done. The scheduler sees that there is a new pod, but let's say that the scheduler doesn't have anything in its cache right now. So it's not able to get the node's information. And so let's say that in this cycle, nothing happens. It can happen, but for the sake of simplicity, let's say nothing happens. Now the connection comes back online. The scheduler again sees that there is an unassigned pod. It goes ahead by its algorithm and assigns pod 3 to node 1. And now the kubelet sees that there is a new pod which is supposed to be running on its node, but it doesn't have it. So it gets that new pod, puts it in its local desired state. And now it says that, okay, my current state, which is just pod 2, is not matching my desired state, which is pod 2 and pod 3. So what am I supposed to do? Let me go ahead and create pod 3. So it creates pod 3. And now things are working great, because not only have you managed to recover from this network partition while a user issued a scale out request, but also you made sure that as soon as this network partition or whatever went wrong has been rectified, you've eventually made sure that the user's new desired state is actually propagated throughout the system, and the actual state of the entire cluster is finally matching the user's desired state. And as this is what I meant by eventually things will work out fine for is what Kubernetes will tell you. And so through this example, we saw what self-healing meant and how it automates some of these things in terms of the user not having to intervene when these sort of unintended changes take place. So let's ask ourselves again, right? What even is this thing called Kubernetes? So if we look at this definition again, and if we highlight those broken down points, it would look something like this. We know why it's good at managing workloads now, as we saw in the example. We know what a declarative configuration means and why did it have to go with a declarative instead of an imperative one, because of all of these unintended state changes that can happen, because Kubernetes is a distributed system and things are bound to go wrong somewhere or the other. It's better to have a system that can autonomously self-heal. And why is it good at automation? Because the user does not have to intervene in most cases. Why is it extensible is the question remaining. Kubernetes is extensible because the API is pretty much constant throughout. What I mean by that is you can have your own resources, or called custom resources. So you can create a resource called foo. You can have a controller for foo, and you can design. You can tell it what you want the desired state of foo to be, and the controller will still work in the same way all of these controllers work, which is the scheduler, the replica set controller, the deployment controller. It will work the same way, and the way it accesses the API is also the same. And in principle, you could design these resources and resources like pods and replica sets in terms of custom resources themselves. So that's how constant the API is. So you can extend it horizontally to your heart's content. So these are the references and resources that I found very helpful. The Kubernetes example of how things work was mainly inspired by this talk, Deep Dive into Kubernetes Internals. I changed a few things to try and make sure that it aligns with whatever we learned before, and also added a few things to make sure the concept of self-healing is as clearly depicted as possible. But these are some of the resources that I found really helpful. So I would highly recommend checking those out. And the slides and source code for this talk can be found here. And thank you so much for listening. And if you would like to reach out for questions or feedback or suggestions or just about anything, you can reach out on Twitter or you can reach out to me on the Kubernetes Slack. These are my handles there, and have a great day. Thank you.